Hello friends, welcome to Best Tutor. This is Rama Vishwanathan. In today's video, we are going to learn something about circles. In the earlier videos, we have learned angle properties, chord properties and so on. In today's video, we are going to learn about tangent properties of a circle. What is meant by a tangent? In the basics of circles, we have seen what a tangent is. Tangent is a line which touches a circle exactly at one point. Now, if I consider a circle, it will have a center. Let me assume that mark the center as O. Then the tangent is a line which touches the circle exactly at one point. This is the tangent. Now the theorem states that the radius is perpendicular to the tangent at the point of contact. What do you mean by point of contact? The point at which the circle and the tangent are touching each other is called as the point of contact. This point is on the circle. So we can always join the center to this point and we can get the radius. Now the theorem states that this radius is perpendicular to the tangent at the point of contact. Actually, the circle has infinite radii. Now we need to prove this. The center of the circle is O. Let the point of contact be P. And then we need to prove that OP is perpendicular to this PT, which is the tangent. We will prove it by method of contradiction. I have already introduced you to the method of contradiction. Let me assume that OP is not perpendicular to the tangent. But we always know that from a point, we can always draw a perpendicular to a line, right? So let me assume that OQ, another line through O, is perpendicular to the tangent. This is what is my assumption. Because OQ is not the same as OP, it should have the point Q outside the circle. That is already understood, isn't it? So let me assume that it touches the circle at a point R. Let me make it clear. As OQ is not the radii which is passing through the point of contact, it is perpendicular to the tangent is my assumption. So it should pass through the circle at some point, or it should intersect the circle at some point. Let me assume that point as R. Now OR is the radius, OQ is a line segment which is perpendicular to the tangent. Obviously OR is going to be less than OQ because Q is a point which is lying outside the circle. Any point which is lying outside the circle should satisfy the condition that the distance between the point and the center should be more than the radius. So OR is less than OQ. But OR and OP both are radii of the circle. Therefore, OP is less than OQ. Right? But we know that the shortest distance from any point onto the line is the perpendicular distance. As OQ is perpendicular to the tangent, it should be the shortest distance. But we have proved that there is something else, some other distance which is going to be shorter than that, which is absurd. That means my assumption that OQ is perpendicular to PT, which is other than OP, is wrong. Therefore, radius is perpendicular to the tangent at the point of contact. This is the proof of the theorem. We were supposed to prove that the radius is perpendicular to the tangent at the point of contact, right? But we have assumed that it is wrong. Then we considered one more line segment which is going to be perpendicular to the tangent, and I proved that that line is going to be greater than this line segment, which is absurd because the shortest distance from a point onto a line is the perpendicular distance. Therefore, OP should be the perpendicular drawn from the center onto the tangent. Hence, radius is perpendicular to the tangent at the point of contact. This is the first theorem we have learned today. The theorem states that radius is perpendicular to the tangent at the point of contact. This is the first theorem we have learned. Now moving on to the next theorem. We have already learned what are intersecting circles. Two circles are intersecting circles. Now I am going to prove that the point of contact of these two circles lies on the straight line segment joining the two centers of the circle. Let the center of the first circle be C1, center of the second circle be C2, and the point of contact be P. Now I need to prove that these three are collinear. This is what is to be proved. I need to prove that P lies on the line segment joining the centers of the circles. How do we prove it? We can always draw a tangent which is common to both the circles. Let me write down the statement of the theorem. Point of contact of two circles touching each other. These two circles are touching each other, then the point of contact lies on the line segment joining the two centers. This is the statement of the theorem. As we have already discussed, the statement of the theorem contains two parts, hypothesis and conclusion. Hypothesis is something which is given in the statement. Point of contact of two circles touching each other. This is the hypothesis. That means the circles are touching each other and they are touching each other at a point. That point lies on the line segment joining the two centers. That is to be proved. How am I going to prove? C1, the point of contact is P. C1P is the radius of the first circle, right? And C2P is the radius of the second circle. Now this PT is the tangent which is common to both the circles. Just now we have seen a theorem that radius is always perpendicular to the tangent at the point of contact. So C1P is perpendicular to PT. Reason? Radius is perpendicular to the tangent through the point of contact. C1P is the radius of the first circle. This is the tangent to the bigger circle. Now similarly, if I ignore this is a circle with a tangent and C2P is a radius. Similarly, C2P is perpendicular to PT. Same reason. Radius is perpendicular to the tangent. Therefore, this angle is 90 degrees as well as this angle is 90 degrees. That means C1PT plus C2PT becomes 180 degrees. Right, 90 degrees plus 90 degrees is going to be 180 degrees. This implies C1, C2 is a straight line and P lies on it. Right, we have proved that the point of contact of two circles which are touching each other is going to be lies on the line segment joining the centers of both the circles. So we have proved two theorems in this video. The first theorem is radius of a circle is always perpendicular to the tangent through the point of contact. Actually, to a circle we can draw infinite radii. We are considering one radius point of contact of the circle as well as the tangent. That was the first theorem we have proved. Right, we have proved that theorem by method of contradiction. The second theorem is if we have two circles which are touching each other, then there will be a point of contact and that point of contact lies on the line segment joining both the centers of the circles. And we have proved using the previous theorem, previous knowledge we have used here. Right. So this is what we have learned in this video. In the coming videos, we are going to learn other theorems based on tangent properties. Thank you.